Okay, class. Welcome to Physics 203, class number 9 on Rutherford scattering. And in this experiment, we'll be examining some experiments about determining the structure of the atom. Once it was known that the electron existed through J.J. Thomson's experiments, as we'll see, it was debated how the atom was arranged, where the electrons were arranged, and evidence accumulated through the process of Rutherford scattering and Lord Rutherford's experiment that we had a charge concentrated in the nucleus. So with that preview, let's get started. So how are charges or electrons arranged in the atom? Well, here's J.J. Thomson, remember the discoverer of cathode rays as electrons or negatively charged particles. And he actually imagined the atom as a sort of what they called plum pudding, after a British dessert where you had pudding in it, and actually raisins were called, it was actually raisins instead of plums, were dotted throughout the dessert. So it was uniform background of positive charge density and dotted with negative electrons. And this had the advantage that it was stable, because the positive charge density would keep the electrons in place. But as we'll see in a minute, it had other disadvantages. The other candidate for how electrons were arranged in an atom was a solar system model, and other physicists, including Lord Rutherford, pictured here, a great British experimentalist, thought it was possible that charges were concentrated, positive charge was concentrated in a nucleus, and electrons were more loosely bound in sort of some kind of outer orbits, like a solar system or planetary system. And this had the advantage that the Coulomb force, the force of electrical attraction, could keep the electrons in orbit. So that was in keeping with known physics. And also electrons might be released from atoms as cathode rays more easily than if they were all jammed together in the nucleus, as in the plum pudding model. So the Rutherford scattering experiment was done in about 1908, and by Rutherford and two graduate students named Geiger and Marsden. And this was the setup. They had a source of what are called alpha particles, which are helium-2+ nuclei, so just two protons basically. And they set up a beam which went through a collimator here, so it came in straight, and it hit a thin gold foil. And they recorded with a fluorescent screen where the alpha particles wound up. And it was expected by the plum pudding model that most of the particles would just go through nearly undeflected. But in fact, what they found was that the particles came through, and while most of them were undeflected, some of them were scattered at very wide angles. And this was hard to understand from the point of view of the plum pudding model. So this is, again, Rutherford's 1908 experiment resulted in alpha particles, that is charged helium nuclei. He used a radon source being scattered at a wide range of angles, at least a few particles being scattered at wide angles by a thin gold foil. And I think, if I remember right, Rutherford said something like, it was if you had these particles which were deflected strongly, it was if you had fired a mortar shell from a tank at a piece of tissue paper, and the mortar shell came back at you, because the foil was the alpha particles were so energetic, and the thin gold foil was so thin that he thought it was that strange that the particles could come back. So analysis showed the plum pudding model could not account for these stronger deflections. It could account for a little bit of spread here, but a model with a small concentrated positive nucleus could, okay? So the plum pudding model came out of favor, and our picture of the nucleus, the one of the atom, the one we normally bring to mind with a nucleus and electrons orbiting around it, was supported. Okay, so let's take a look at the analysis of Rutherford scattering. There's an awful lot of algebra in the text here. I just want to present you with the main results and the two main results and what how some of the relationships between those results, between variables in those results. So here is a diagram of a scatterer. This would be an atom in the gold foil. And this is an incoming alpha particle, these particles coming in. And B, as we'll see in a second, is called the impact parameter. It's the distance between the scatterer, the perpendicular distance between the velocity of the particle coming in and the scatterer. Okay, so it's the point of closest. It would be the point of closest approach if the scatterer didn't exert any force on the particle. Okay, so you can see there can be a range of impact parameters B, and then theta is the angle as measured from the positive x-axis of the deflection. And Rutherford and his collaborators had detectors spread all over the place because of that fluorescent screen that they had, so they could detect it in all directions. Okay, so that's the impact parameter and the scattering angle theta. And the relationship, which is derived by a lot of Newtonian mechanics and Coulomb forces, which I won't take you through the details. You're welcome to look in the text at the details of the derivation, but I just want to present to you the main result. And that is that the impact parameter is equal to the atomic number of the incoming particle. For the alpha particle, that would be 2. The atomic number of the scatterer, Z2, the electron charge squared over some constants, 8 pi epsilon naught, times the kinetic energy of the particle coming in the denominator, times the cotangent of theta, the scattering angle, over 2. Okay, and here again are just the definitions of what's appearing here. B is the impact parameter. Again, this perpendicular distance that the particle would follow if it was not scattered. Z1 and Z2 are the charges on, or rather the atomic numbers of the particle and the scatterer. K is the kinetic energy of the particle, and theta is the scattering angle to the detector. And so let's just take a look at a couple of main aspects of these relationships. We have B is equal to the cotangent of theta over 2, and that may not be a familiar function, so I've plotted it here. It starts at theta equals 0, starting at a high value, and as theta increases up to pi, which is the maximum scattering angle we can get, we would get theta approaching 0. And so that makes sense because we expect that for, since B is proportional to cotangent of theta over 2, as theta starts at 0, we get the maximum number of particles at theta around close to 0. We get the maximum number of particles coming through. And as theta turns around to pi, we get fewer and fewer particles, that would correspond to particles which are turned around and deflect it around. In terms of the kinetic energy, at a given angle theta, the more energetic the particle, the more kinetic energy the particle has, the smaller the impact parameter would be needed to deflect the particle, because the particle would have a lot of energy coming in, so it would need to experience a lot of electrical force to be deflected to a given angle theta. And Z1 and Z2, on the other hand, if for a given angle theta, the more charge are on the particle and the scatterer, the stronger the electric force, and so the larger the impact parameter would be sufficient. It could be farther from the scatterer and still get to the detector. Okay, so you can just remember this relationship, and hopefully we've gone over some of the dependencies here. And again, if you're interested in the derivation of this, you can check in the textbook. There's another more full derivation of Rutherford scattering. This one's in 3 dimensions instead of in sort of along 2 dimensions. Now we imagine the particle coming in along or around a ring or annulus, so it can come in any around a cylindrically symmetric ring here. Here's the scatterer, and again we have the same impact parameter and the angle, but it can come out at any, it comes out at a certain angle theta, but at any angle phi, we call it. So around this sort of ribbon here, we would see particles being detected. And that's the physical situation. Of course, it's a 3-dimensional situation. This is the equation for Rutherford scattering, the famous Rutherford scattering experiment. It looks like a big mouthful, so let's try to break it down a little bit. Again, Z1 and Z2 here are the charges on, or the atomic numbers of the particle coming in and the scatterer. K is the kinetic energy of the particle coming in. And theta is the scattering angle. B, again, the impact parameter. Ni here is the number of incoming particles. So in the original experiment, the number of alpha particles which were sent in. N is the atoms per unit volume in the target scatterer. Okay, so gold has a certain number of atoms per unit volume. T is the thickness of the scattering film, and R is the distance from the scatterer to the detector. So let's take a look at this formula. This formula expresses the number of particles which are to be expected to be detected at an angle theta, where an angle theta, remember, is the angle theta can range. Theta is this angle, but it can it counts if it's anywhere around this circle. That would be the angle theta. So it would certainly be proportional to the number of particles that we send in. The more particles we send in, the greater the number of particles we'll see at any given theta. It's proportional to the atoms per unit volume in the target scatterer. The more atoms, the more scatterers a given incoming particle sees, the more likely it is to be deflected. It's proportional to the thickness of the scattering film. Again, that means it will see more potential scatterers, gold atoms in the original experiment. And let's see. So just like before, the more charge is on the scatterer and the particle and the scatterer, the more deflection we expect to see at a given angle, because we get greater Coulomb forces. On the other hand, the more kinetic energy a given particle has, the harder it is to deflect. So we expect to see less at a given angle theta, or we expect the dependence to be inversely proportional to the kinetic energy, because it gets the higher the kinetic energy, the harder it is to deflect it at to a given angle theta. The more sort of inertia the particle has coming in, and the less effect the force will have. And then this angular dependence is the interesting. It's the fourth power of the sine of theta over 2. Okay, and that is a decreasing function of theta, as we would expect. And I can show you that here. These are results not from Rutherford's initial experiment, from a student's experiment, where instead of alpha particles, protons, which are charged particles, were sent in, scattered by a gold foil. And you can look at the scattering angle, which goes from 0 up to 180, or 0 to pi, 0 being this direction, pi being all the way around the other direction, and plot the number of detected particles at each scattering angle. And we see that the number of particles per scattering angle fits this function, sine of theta over 2 to the -4th power. Okay, so I expect you to be able to use these, to know what the variables are in these relationships, and to be able to use them to calculate things. I don't expect you to understand I don't expect you to understand the derivation of them. That's fairly involved and beyond the scope. Well, not beyond the scope of this course, but I don't want to get into that kind of detail. So this agreement between the number of particles seen at a given angle and the this prediction coming out of the analysis of Rutherford scattering was seen as a victory for the solar system model. So for this solar system model here, because only a small positive nucleus could exert enough force to deflect particles all the way back at these severe angles. The plum pudding model just can't generate that type of net backward force. Okay, so the solar system model, is that the final answer? Not quite, because of the problem of acceleration. Now, you may be familiar from Physics 202 with the fact that accelerated charges radiate. This is an example. We have a particle here which starts at the origin. Starts at the origin here. You can see the lines of electric field lines coming out where it was at the origin, but then it accelerates to the right. And as it accelerates to the right, and it's at this position, it has electric field lines coming out from its current position. But there's got to be a transition between the original field lines, where it was originally before it accelerated, and the field lines after it accelerated. And that transition point is this kind of these perpendicular lines here, and that discontinuity between the first field lines and the updated field lines actually turns out to be an electromagnetic wave, which carries away energy. So when a particle is accelerated, because of this sort of phenomenon here of this transition between where the field lines would be if it hadn't moved and where the field lines are once it has moved, this transition region actually carries away energy. It looks like an electromagnetic wave. And so this leads to a problem, because in the in the solar system model of the nucleus, we have an electron which is accelerating, right? It's going around the nucleus. So we have acceleration, that centripetal acceleration in the solar system model, that counts as acceleration. So that energy, because of that acceleration, energy is radiated by the electron, just like this energy being radiated by this linearly accelerated charge here. And so the electron would lose kinetic energy and spiral in to the nucleus. And it actually happens very quickly. We'll do a problem in class just to estimate how quickly that can happen. And this is called the death spiral of the electron, which is one of my favorite terms in physics. So even though, so to summarize, even though there was a competition between the plum pudding model, where electrons were sprinkled throughout the nucleus uniformly, and the solar system model, where electrons were in orbit, and it looked like from Rutherford's scattering experiment, from his backward deflections and his quantitative agreement with his formulas, that the solar system model was correct. However, we still have this problem that in the solar system model, the electrons accelerate around and spiral in toward the nucleus, thereby radiating away their energy. And so there's still a mystery to be solved there. And the first step towards solving that, the need for what we call the stability of the, this should say the stability of the atom, or the electron, I suppose, because it's the electron in its orbit, leads to the Bohr atom, which we'll talk about next time. All right, thank you for your attention, and I will see you in class.